in the middle of the proof of sort of this technical result that showed the sort of stronger version of the RE condition. So this uniform result for Gaussian correlated design. Okay, so again, to remind you, you were trying to prove something like this, and you saw that if, or you're going to show that if this holds, for example, you have the RE condition for subset S for which n is bigger than S log D, where S is the number of non-zero elements or the cardinality of the set. But we also saw that this is useful to prove things like Orthogonal inequalities, where you remove the assumption that theta star is a sparse, and then you can sort of analyze more general, let's say, structures like the LQ ball sparsity. So it's a very useful condition to have, and it's quite strong. The question is that is it going to be true? I mean, what other conditions that we need? And the point of this result is that it is sort of true with high probability for any correlated design, as long as the sigma is non-singular, more or less. So to remind you what we did, this is the notation that we're going to use. The sphere in Rn, this is the L2 sphere. So the locational points that are at distance 1 from the origin. So it's the boundary of the L2 ball, unit ball. And then we saw that because I can rescale everything, or the theta arbitrarily, I can assume a particular scaling. So we assume that this quantity is 1. And so the problem reduced to, after some considerations, reduced to showing this over theta that are in that set, capital theta. Capital theta is a set where, we define it in this set. So that's the set where our normalization condition holds. And then some rearrangement, further rearrangement, we wrote it in this fashion. So we want this inequality to hold. So that's the good event. So the complement of this, we want to show that's small. So we ended up having this event, right? So this was the event that we want to control. We want to say that the probability of this is small. And what we did was use a technique called Tealing. So to get rid of the fact that there is this variable here, so we subdivided the 0 to infinity interval into these progressively longer intervals. So 0 to mu, mu to 2 mu, 2 mu to 4 mu, and so on. And in each sort of shell, let's say, we have like a tight control of what G norm 1 of theta is. So the first step is that the infimum is less than 1/4 if there is one of these let's say L's intersect with theta, for which the infimum, or over which the infimum is less than 1/4. So we wrote the event of interest as the union of these smaller events. And then over these smaller events, I can sort of lower bound this by 2 to the L minus 1 mu. So because this holds, then the lower bound has to be less than 1/4. So this implies this, and so this implies that. So there's a logical implication, which means that this event is inside the other event. And so this is now sort of clean. So we have like the L2 norm of a matrix times theta, infimum over, but the set is complicated. We want to control this. We want to say that the infimum being less than this is small. So basically you want to say that the infimum is large with high probability. So this step is where we did the variational characterization of the norm. So we replaced the norm L2 norm with, did I have it here? Yeah, so there's this idea that I can write the L2 norm as the maximum of the inner product of x and u, where u varies in the sphere. So this is sometimes called the variational characterization. This follows from the Cauchy-Schwarz. Okay, so we replace norm to x theta with this variational characterization. And then we also replace x with w sigma 1/2. We went over why this is true. So now w is a matrix n by d, which is filled with IID standard normal entries. So it's a very nice uncorrelated, sort of everything independent matrix. And then we absorb the sigma 1/2. So you can see sigma 1/2 times theta. I define a new variable v. And then sort of push the complexity of sigma into that variable. So now if you plug back in everything, you get that inf and then sup over u, and then u wv over root n. V has a certain set in which it lies because I know that so this is basically theta. Right? I know that theta has to be in capital theta. So sigma 1 negative 1/2 v has to be in capital theta, and also sigma negative 1/2 v has to be in I sub L. That is I sub L. And you can see sigma negative 1/2 theta. So v is being in theta. Theta means so theta, recall, is a set of all things that for which sigma 1/2 theta is 1, right? So there's a set of all theta such that sigma 1/2 theta L2 is 1. And if I replace it with sigma negative 1/2 v, I'm looking at all the v's for which sigma 1/2 times sigma negative 1/2 v is L2 norm is 1. So you can see easily that this just simplifies to the fact that v has to have L2 norm 1. So this condition is basically this capital V is simple. It's just the sphere, but now the sphere is in RD. So U is in the sphere in Rn, V is in the sphere in RD, so dimensions match. The other index set we're not gonna use. So this would be complicated, but I guess we're not gonna worry about this. It's just enough that V is in the sphere, on the sphere. So this was more or less the reduction that we did last time, right? Okay, any questions? As this? So the significance of this is that now this quantity here can be viewed as a process. If I define like a random process indexed by 2 indices, which is given by this, it's a random process. It's a Gaussian process because each one of the marginals is. So you know these are. Can I say that U, like Y UV is a Gaussian? Is it a valid statement? Like it's a fixed U and V. Why is it a Gaussian?
It's like W discussion. The product of U, or like it's a linear combination.
Yeah, great. So this is basically, if you expand it, it's just UI, Vj, Wij, or root n. It's just a linear combination of the elements of W, and these are jointly Gaussian because they're independent. So for any U and V, these are Gaussian, and the thing is jointly Gaussian as well. So it's just everything is based on this. So it's a Gaussian, really a Gaussian process. But the thing is that for different U's and V's, if you take Y U V and then Y U tilde V tilde, they're not independent. Okay, there is some sort of a correlation structure. So it's a very genuine process. And I mean, it's a linear process. We can ignore the linear part, but it's an example of a Gaussian process. So, okay, before we get there, we did one more simplification. It's just this was FL. then we multiply everything by a negative sign. So when you move the negative past these things, you flip. So if you move the sign past the inf, you flip it to sup. You move it past sup, you flip it to inf, and then there's a negative sign here. I can absorb it into u because u is symmetric. And then this side is the sign is flipped. Okay, now at this point, so we have this process. So this is sup inf of a Gaussian process. And then we broke out this like technical device, which I'm not proving, and I'm actually not giving you the exact statement, but the statement is exactly what is there. So this is saying it's a nice result that says that if you have two processes like y uv and z uv, they're both Gaussian, both indexed by the same indices, and if these inequalities hold, what this is saying is, if I haven't done any mistakes, is that if I change both indices, in general, this side is less than this side. If I fix one of the indices, like the second index, and change one, then I have equality. If some sort of a result like this hold, in the study of Gaussian processes, this quantity defines a metric. If you compute this, it just defines like it's a measure of how close these indices are. And it induces a metric on the space, the index space. So this is comparing the metrics of the two Gaussian processes. But it doesn't matter what it means. It just says that the increments of the process are sort of controlled. So this process, the increments of this are bounded by the increments of this. So this is sort of, on average, is larger. And this is just a technical thing. Like if I fix one of the indices, the equality, I'll let you verify this. Hopefully, post it as a homework problem. You can. So the z that we take is the simple process where you have this decoupling. So you take g and h to be normal, the standard normal, and then define this process. You can see this is simpler than this because it just combines every element of the matrix. It has two separate independent vectors. The only thing that we need here is, so this T is this index set. The only thing is that U is on the sphere and V is also on the sphere. The fact that U and V are on the sphere, and with these two definitions, we can verify this. This is a good exercise for you to try. If these conditions hold, if I haven't had a typo there, then Gordon's theorem says that sup inf of this process in expectation is upper bound, like lower bounded by sup inf of the other process. That's the main thing. So if I take the expectation, this is like a property of the process is a random variable. The expectation is bounded by the expectation of this. These are called, let's say, this is an example of a Gaussian comparison inequality. Gaussian comparison. It's one of the more complicated versions. There's the Slepian lemma, or sometimes called Fernique, pseudo-called Fernique. Slepian. Who you should attribute these is debatable, but there are different versions. There are simpler versions of this where you just compare the supremum. But it's interesting because it compares the minimax quantity. In any case, let's say you agree with this. Let's say this holds. These conditions satisfied. I can compare these two. Now I can compute. If I define this was what was it? G U plus H V divided by root n. Now I can simplify this side. I just plug this in, and then you tell me what is the next, why the next step is valid. Okay, so that's this guy, right? So now why can I write something like this? Yeah.
Separated the variables
Yeah, so basically the different variables are separated. So if I take the inf, this part comes out. So you take the inf of this, you get this, and then this comes out, and then there's a soup, and this whole thing comes out as well. So it's easy to see that when you apply this, it just breaks into two pieces: expectation of the soup over this plus expectation of inf over this. Does this make sense? So what I'm doing here is, so you have expectation soup inf over v over u. Let's say forget about the root and I have like gu plus hv, right? When I do this, this comes out, soup over v. hv comes out from the infimum, right? So you get inf over u gu, right? And then this whole thing doesn't depend on v, right? So now this comes out of the supremo, right? So you get, this is equal to expectation inf over u gu plus soup v hv, and then the expectation sort of is linear, right? So this comes out of the supremum. Expectation is acting on everything, so you get the expectation of this part plus the expectation of that. So that's the main sort of advantage of this process. I can decouple taking the soup and inf. So this inf is, I replace it with that. So why this is true?
U has to point in the opposite direction of G because so minus G.
Right. Is that what you were saying?
Oh, yeah, I was just gonna say inf f equals minus soup of f.
Oh, okay. So yeah, both are good. Okay, so yeah, so let's try. Both works. So we can say inf. So as you pointed out, if we take, we want to make the smallest, it's like the Cauchy-Schwarz in the other direction. So you want to take this to be in the direction of G, but the negative direction. So you get like G over norm of G, and then simplifies to that. Or you can say inf GU is negative, right? Soup negative u in Sn minus 1, right? And then this is going to be, the soup would be the same as the soup of G and U, let's say U in Sn minus 1. This soup is negative. The soup is from this idea, right? This would be negative G2. This is also nice. Okay. So in any case, this would be negative. Now we're stuck with this one. Okay, now this is the tricky part because now I'm going to use this JL because I have, I'm going to use the fact that on this IL, basically the L1 norm is controlled. So that's the key advantage of basically we're sort of restricting ourselves to these controlled L1 shells. So now that's where I'm going to use that. So this is again a little bit tricky because I have to remind you what this JL is. So JL is the set of all V such that sigma minus 1/2 V is in IL, right? And IL was the set of all theta such that G, what was it? Yeah, G theta 1 is in 2 to the L minus 1 mu and 2 to the L mu. Okay, so let's see how it works. Yeah, okay, so there is this piece which is, again, you can show the this one is further lower bounded because there's a negative sign. I want a lower bound to get an upper bound. So this is lower bounded by root 2n divided by pi. This you can verify for yourself. We know that the norm of G2, if you recall, is like close to root n. It's like upper bounded by root n, and it's also lower bounded by constant times 2 root n. This is not difficult. This is sort of, you can compute it by integration, or you can do by sort of approximation. Let's accept that. That's I can assign it as a homework problem actually. So this is taken care of. We come back to this. This is basically if you plug in root 2 and pi, you can see this is going to be a constant. Now let's take care of this. This is going to be like that. I'm going to recover the theta. So V intersect JL, we call that, what was V? V was sigma. V was sigma 1/2 theta, right? So I'm gonna replace this with sigma 1/2 theta, and then it means that theta is in theta, capital theta and IL, because that's how this was. So this was like a translation of this set to the V domain. So we're back. I replace it with sigma 1/2 and move sigma 1/2 to the other side. This is doable because what? Because of the symmetry. Yeah, so this is like self-adjoint. Or if you're not comfortable, just write it as a transpose and things would work out. Okay, now this is the tricky part. I'm going to bound this by the infinity norm. So this, the whole Lorentz inequality. So this is bounded by sigma 1/2 h infinity and then theta L1. Because I have control of L1 here, I'm going to get the L1 norm here out. So then take the expected, so we take the soup, this comes out, and the soup goes over this, and then there's an expectation. Okay, so the soup here, you can see this G was a linear function, basically, if you recall what G was. G was this quantity. Okay, G is basically GT. I'm going to write it as 2 rho. I drop the sigma root log d over n. It's a linear function. It's increasing. So if you just copy paste this here to remind us what it is. There's also a G inverse. So on IL, norm theta 1 would be in G inverse 2L minus 1 mu, and because it's monotonic, so G inverse 2L mu, right? So over that shell, theta 1 is bounded by G inverse 2L mu. Okay, so the supremum over this, I don't care about theta here, it's the G inverse 2L mu. And then what I'm doing is, so is this part clear? So that's the bounding the supremum here by this. That's because of the construction over this shell. L1 norm is bounded by G inverse of the endpoint of the interval. The first one I'm bounding by G1. So G1 is just, it's a convenient way of writing this quantity, 2 rho root log V over n. So I'm saying that this is bounded by 2 rho root log d over n. Is this obvious to people? So the root n is here. So what I'm claiming is that basically the expectation, so you're claiming is the expectation of sigma 1/2 h infinity is bounded by 2 rho root log d. Let's see if anyone can argue this. No, yeah, it's not diagonalized. It's the diagonal entries. So rho squared is max over I diagonal entries of sigma. So let's see if anyone can argue this. This is really the key sort of step. So we have rho squared is max, and then I have expectation. And then I get sigma plus 1/2. I want to claim that this is 2 rho root log d. That's where we get the log d here. Okay, instead of a high dimensional business, we have a log d, which is nice. So h, what is h? H is standard Gaussian vector. So h is normal between 0. How should we argue this?
I think we have a homework problem like that.
Really? We have it, so probably I shouldn't solve it then. Have you guys thought about it? So this Gaussian, standard canonical Gaussian basically has a very nice property, which is called rotation invariance. Okay, it's invariant under orthogonal transformations. So what is an orthogonal transformation? Anyone? Orthogonal matrix?
A is orthogonal than A transpose.
Right. Equal to identity. Yeah. So let's call it U. U transpose is equal to U transpose U identity. So where do these things sort of occur? So this is an orthogonal matrix. U, let's say, transpose H. What is the distribution of this? First, let's figure this out. And covariance?
It should still be identical.
It will be U transpose U, yeah, which is identity, right? So what this like argument shows, if it's not, you're not comfortable trying to like prove this, this is like a transformation of a Gaussian or any vector linear transformation. So it does this to the covariance. So you get, let's say if this was A, you get A transpose here. So A covariance of this would be A covariance of H, A transpose. That's the general formula. In this case, covariance of H is the identity. So this little calculation shows that if U is orthogonal, U transpose H has the same distribution as H. So this is what rotation invariance means. So these orthogonal matrices are rotations or reflections in RD. So this is saying if I rotate. So you know, for example, in R2, the level sets of this distribution are like circular. Right. So if I change the rotate the axes, the distribution doesn't change. If there was like a if I also reflect, it doesn't change. So it's invariant to rotation or reflection. If the covariance matrix was not identity, then it wouldn't be, right? So it would be like something like this, and then it's not rotation invariant. But the so-called canonical Gaussian measure in RD is rotation invariance. So rotation invariance of Gaussian measure or Gaussian distribution. There's also something else which is rotation invariant, and it's the L2 norm. So the L2 norm is also rotation invariant. These go hand in hand. So the L2 norm has this property that if I rotate, it doesn't change the L2 norm. So the L2 norm and the canonical Gaussian, they're sort of closely related. So you can see this is like, this square appears in the PDF, right? So the PDF of H, let's say, is e to the negative H squared over 2. And so if I rotate this PDF doesn't change. Okay. Either case, and in either case, we can prove it without the PDF as we did here. So where do these orthogonal matrices often come from? Where is like a good source of these orthogonal matrices in linear algebra? Right? Singular value decomposition or eigenvalue decomposition. That's usually what produces these. We can also like make the other sources, like take a matrix and do the Gram-Schmidt on the columns. So you make them orthonormal. So these are basically, the columns are orthonormal, means that they're unit norm, unit L2 norm, and they're orthogonal. So the columns sort of give you an orthonormal basis of RP. And when you do, I can do, let's say, eigendecomposition of any symmetric matrix. The sigma is symmetric has an eigendecomposition where U is orthogonal, right? And so this is the EVD. This is orthogonal. And this is diagonal. So lambda, the diagonal entries are the eigenvalues. So D. And then the U, you have U1 up to UD. These columns are the corresponding eigenvectors. So U1 would be the eigenvector corresponding to lambda 1, U2 corresponding to lambda 2, and so on. And usually you order the eigenvalues in decreasing fashion, but it's not necessary. So we have a decomposition like this, okay? So if I have a decomposition like this, what would be sigma 1/2? Anyone knows? Sorry? This is interesting. So what is the definition of sigma 1/2?
Sigma 1/2 squared is equal to sigma.
Yeah, so this is valid as well. This is like a asymmetric square root. So you can define a square root to be any matrix such that A transpose is sigma. Then there are many choices. This satisfies it, because if I transpose it, I get lambda 1/2 U transpose, and then we get this. So this is an asymmetric square root, usually the sigma 1/2. So asymmetric square root. Sigma 1/2 is usually reserved for the symmetric one, which is going to be U lambda 1/2 U transpose. If you multiply it by itself, I mean, if A is symmetric, so symmetric A means A transpose is the same, so A squared is sigma, which is what you expect a square root to be. Anything that root of square is the original thing. So if you do this, you get U lambda U transpose, and then U lambda 1/2 U transpose. U transpose U goes away. So you do the calculation. This turns out to satisfy this. Okay. Now can maybe anyone tell me how to prove this? Actually, it's not going to be helpful. Is this going to be helpful? No, 2 norm is too big. I'm going to leave it as an exercise, actually. If this is not going to be helpful, because U transpose H is going to be nice. If I plug this in here, U transpose H is, again, distributed like H. But the U here is troublesome, because the L infinity norm is not, I just realized that this is not going to work. So I'll let you do it. U sigma 1/2 U transpose H. I can replace this with H, okay? It has the same distribution. So I can say the distribution of this, the expectation is the same as the expectation of U sigma 1/2. Oh, sorry, not sigma 1/2. Lambda 1/2. Lambda 1/2 what? H infinity. But then I can't get rid of this. If I could get rid of this, the reason why I can't get rid of this is because infinity norm is not rotation invariant. If I could get rid of this, then it would be nice, because this is diagonal, then this is 3 scales the edge.
Can we also bound it by separate, like, to the operator norm and
Okay, interesting.
expected value of separate.
So you could do infinity, infinity.
Yeah.
And
the
then,
second one is like,
right, so you get, this is going to be infinity, infinity.
right?
Oh, right.
Yeah.
There is lambda 1/2, right?
And then that would be upper bound by the largest element.
Which one is upper bounded?
Wouldn't that be, so that's the maximum absolute value of the element, right?
Yes.
And
So,
we can upper bound that by the maximum element of the Rotational matrix times.
yeah, so the diagonal matrix times this would be just rescale every element by the, so this would be, this is nice, but I'm worried about the first term. So let's see what this does. This would be expectation. Can you tell me what
Largest
maximum?
square root of
No, the lambdas, right? So these are hi.
I'm not sure what to do about it.
So this would look like this, okay? Because lambda 1/2, lambda is diagonal, right? So lambda 1/2 would be square root. Lambda 1/2 would be root lambda 1, root lambda 2, root lambda d. And when you do like multiply a diagonal matrix by a vector, you just rescale every row.
The operation oh, that would be, yeah, the norm is not in rotation invariant. I was thinking we could just write the definition that would be 51, but that's only the case of its rotation invariant. Write the definition, maximum ux over x, and then ux, if it's rotation invariant, would be equal to x and x over x.
Yeah, it's not. Yeah, so.
That could be upper bounded by set norm 2, and then that could be cool.
So this in general is an upper bound.
By 1.
No, so the operator norm of U is 1, but there's generally this inequality if I recall correctly. So you get this times U1. You have my notes on like matrix.
So that norm infinity, that's equal to maximum infinity norm ux over x. Let's say we just like that definition, and then that would be upper bounded by
L2 norm,
two norm.
but that's not going to help.
Yeah, I see.
You can bound it by L2 norm, and this would be like this, but then
Then,
this would be like root D. Yeah, this is not right. This is a little bit problematic here. We can try to figure out what this is, but you can think of what. So this is related to the maximum absolute value of the rows or columns. I forgot which one it is. There are cases like if you use the identity, this would be one. But just do it for yourself. See, like there could be like cases where this is big. That's my guess. But how do we deal with this? Let's say, if this would work. You can get a hint because I'm having the eigenvalues here, but this row is related to the diagonal entries, not the eigenvalues. So you have to do something else. But the idea is similar. So if this was good, I could get rid of it. Let's say this was 1 or bounded. Then I would end up with this. The key is basically something like this. How do I control something like this? These are sub-Gaussian, right? The expectation of a maximum of a bunch of sub-Gaussian random variable scales like root log D, right? So this would be like maximum eigenvalue comes out max lambda I root, and then I get expectation of max hi from 1 to D. This would scale like root log D. That's how you get the root log D. Okay, but this is problematic. So you can backtrack everything and do something else. But there's this sort of essential idea is that if this was identity, like the diagonal, then this would work. So you have to somehow reduce it to the diagonal case. But I'll let you do it as a homework problem. It's trickier, it seems. Okay, but this you remember. Expectation of the maximum is root log D, so that's the essential idea. So if this was diagonal, you can immediately get this. This was diagonal, then this would be the square of the diagonal. So this there's some sort of squared here. Yeah, we're missing a square as well. Yeah. So something is missing, but no, actually not the square. Yeah, this is like. This is fine. It's just root. The square is not a problem. Okay. Think about it as a homework problem. But in the end, this is true. You get G1, and then what we get is, so if you think about the G, G inverse is basically, so G is like AT, and then G inverse T would be 1 over AT. That's how the inverse of a linear function works. So if I multiply these two, so I get A's cancel out, so you get 1 times this, you get 2L mu. That's sort of the nice thing. So in the end, this part is bounded by root 2 pi, upper bounded by that because it's lower bounded by that, and this is bounded by 2L. So that's the final bound on the expectation. Okay, so we're almost done. The KCL was the expectation of this, but you also need to control the random thing. So I have a control over the expectation of this. This is a random variable. I have a control over the expectation. Now I want a high probability bound. So how do we generate a high probability bound from the bound of the expectation? Use concentration inequalities, right? So you could use a concentration quality. Is there a concentration quality that we can use? This is not like a nice looking function. So if it was just this part, this would be the sum of a bunch of IID variables. But this is a very complicated function of W. Is there anything that we can use here?
Can we separate the first supernode and the supernode greater or equal to T?
T,
Then it's equal to the probability of at least one B existing. that
Yeah.
satisfies that. And that would be smaller or equal to the union, we use the union bound.
yeah,
And afterwards, writing the union bound, we will have the increment would be the probability of each of those elements. That greater or equal to T, and then that means all elements.
Yeah. That could work. The issue is that probably the union bound that you do, you need first the technique that you're going to develop next, because this is the continuous set. It's like discrete, right? So you have to do union bound over an infinite set, over the sphere. You're going to do a similar thing shortly, but you need some more tools to do it. Basically, you have to discretize the V here is the sphere. So you have to discretize using a net, epsilon net, and then you can do linear. We're going to do exactly this for upper bounding a quantity like this. We want to have a yeah, like if this int wasn't there, that would be a good idea. But then once even if that works, then the int would be a little bit tricky. It's just the intersection of all of those, and then these events are not independent, right? So you need all of these to be bigger than this, or just let's say even if I discretize this, but the events are not zero. It's an intersection of a bunch of dependent events. So you're going to have a lot of troubles. It could work, but I don't have a like something other like I don't know how it could work. It may work, but it would be maybe much more tricky. So we can use a very nice property of Gaussian distribution. So did we talk about a kind of concentration inequality for Gaussian? Anyone remembers? Yes. There's a reason why we're doing it for the Gaussian case only. And that's exactly because of because of these comparison inequalities, which was for Gaussian processes and not general processes. The other one is that I can argue that this is a Lipschitz function of W. Okay, so if you think of W as a giant vector, this whole thing is a nonlinear function of W, and then you can show that this is Lipschitz with Lipschitz constants 1 over root n. So 1 over root n comes out, the rest is 1 Lipschitz. And then I can just use the dimension independent, sort of the best possible concentration that you could get in the business, and then I'm done. So this show as an exercise, probably I'll assign it as an exercise, show that QCL, that's sort of this quantity, I think I called this QCL. This guy, QCL, is a Lipschitz function of W. Okay, QCL is a Lipschitz 1 over root n Lipschitz function of vec W, which is the entire vector. So I get the QCL bigger than this quantity plus delta is less than QCL bigger than expectation of QCL plus delta. That's the upper bound on the expectation that we had. Okay, because this is upper bounded by this. This implies that. And this is the Gaussian concentration. Okay. It's just a very simple step. Just takes care of like a big challenging problem. Okay. Once, but you can see just this step is much simpler relative to all the things that we have done to control the expectation. So the Gaussian concentration, if you have a Lipschitz function, usually immediately reduces the problem to controlling the expectation itself. Once you have it, just one line, you have a nice concentration result. Now we have to like choose this delta. again, this is the tricky part. I have no intuition here at the moment. But let's say C is, take C to be root 2 pi minus 1/2. This is bigger than 1/4, let's say. And then I take delta to be C plus 2L mu. If I do that, so what would I get? So plug in delta here. Then these two cancel out. This cancels out with this. What do I get? I get, oh, it doesn't cancel out. Right, doesn't cancel out, you're right. Twice, yeah, right, so you get, right. So you get 2L plus 1 mu minus root 2 pi, 2 more pi. And then, so how do I get this? So let's say this is that, right? So that's this guy after we plug in delta. Can you say that again? How do I get it?
So like C is equal to root 2 over pi positive. So that cancels with the.
Oh,
And then
right.
we just have the extra factor.
okay, good. Right. By definition, sort of basically. Let's call it. So by definition, I get this. This is, there is no inequality here. And then I also have to plug in delta here. You can see you get negative n times c squared over 2. What I'm doing here is that, so e to the negative c plus 2L mu squared over 2. And then I upper bound this by c is squared. There's an n as well here. Too many like little steps here. So plus 2L mu squared divided by 2. I just drop the cross term. There's a cross term you can drop, you get an upper bound because these are positive, right? And there's a negative sign. So the cross term would have like a negative sign here. I can drop it. So I get this, and then this just separates into two pieces. This part turns out to be n e to the negative n 32. I guess c. We haven't specified c. Just pick c however you want. We can just take it to be something to make it 32. It just doesn't matter. It's just a constant. You can see it's e to the negative n times some constant, which is good enough for us. And then this part is you further bound 2 to the 2L by lower bounded by 2L, and mu is 1/4, so you get 16. So if I lower bounded by 2L, just plug it in here, you get an upper bound. So you get this. That's the final bound, and you can see there's this geometric business going on here. So now the probability of, I need to control the union, if you recall. The union of this, there's this union bound here. And then I just plug in here. And then this guy is a geometric series. Okay, that's the Tealing part of the argument. So you don't pay an extra factor here. So e to the negative n. 16 to the L. That's a geometric series. You get basically 1. So this entire thing would be 1 over e to the negative n 1/16. This is really doesn't matter. So when n is big, this is up to a constant e to the negative n over 32. So the overhead from the Tealing, which is this part, just is a constant. Okay, so that's how it's finished. This part is a little bit tricky. I don't have much intuition, but if you do it properly, basically you want this to be less than this, sort of the order of this. But at the same time, you want this to also not blow up. So these choices work. Just go through this part for yourself. It's not difficult. But you can see the Tealing here allows you to sort of, actually this is much better. So it's 2 to the 2L, it drops very fast. But this allows you to sort of, you can see the effect of Tealing is just that you have this extra factor here, which is gone. Okay, so this was a very, I would say, technical result, but if you go through it, it's just a lot of tricks that you would have to like do if you want to do this stuff like at a research level. This is, I would say, this was like fairly recent, a few years ago, like 10 years ago probably. And for example, extending this to sub-Gaussian designs is not easy because you've seen we use very special properties of Gaussians. But it's often good, a good first step to assume things are Gaussian, see what you can do. And you can also get a sense of how difficult the general case would be. But once you have a result, then you can try to say, okay, so I have this for Gaussian. Now, what can I say for sub-Gaussians? Can I like recover some sort of a result like this for sub-Gaussians, for sub-exponentials, and so on and so forth. Okay, questions? Okay, so so once you see this, the rest is going to be a walk in the park. So we're gonna like simplify. Okay, I don't have, yeah. So any question? We can come back to it later, but some of the elements I think you'll see in the homework problems. I should remember to just assign this Lipschitz part as well. Now let's go. I want to finish this chapter. That's chapter 7, I believe. So we talked about the consistency of the lasso. So parameter consistency of the lasso. Parameter consistency of the lasso, or if you want deviation bounds on theta. So we showed things like theta hat minus theta star behaves nicely, like root s log d over n with high probability. So this required basically RE condition. Required RE condition. So this is for SS sparse vectors. And we also saw a version for general Orthogonal inequality, which I don't write. And then LQ sparsity follows, which was this like log d over n to the 1 minus q over 2. This is again a nice rate because it's logarithmic in d. With higher probability for this, we required that result that we just, so uniform, let's say RE if you want. Uniform extension of RE. The result that we just proved. And sort of that's the extent of the things that you can do with the parameter estimation. There are other problems that you can solve in the context of linear regression, or other sort of performance metrics, basically. One is the sort of prediction bounds. So if you don't care about the actual parameter, but you want to have a good predictor. Okay, so what do we mean by prediction? If you recall, the model is in the linear regression model is something like this, I from 1 to n. So these are observations on like a population level version. This is just y theta star x plus epsilon I. This is some sort of a function. Let's call it f theta star of xi. So we are modeling the relation of yi and xi, yi a linear function. Okay, so if I care about estimating the value of this function, not necessarily the theta star itself, then I can do better. And if you've seen classical regression, this shouldn't be a surprise because the multicollinearity, for example, prevents you from estimating theta star ball, but theta star transpose x is well defined. So the idea is that so if you consider, maybe mention this, if you have an estimate, and if you look at, for example, yeah, so if you define this norm, and this is called the empirical norm of function. If you look at the empirical norm of an estimate, so this is basically 1 over n summation I from 1 to n, f theta hat xi minus f theta star xi squared. This is an approximation of the L2 norm. Okay, population level L2 norm, the p of x, let's say, if you want, if xi is a random. So this is a metric that we can like use to measure the predictive performance, how well I'm estimating the functional relation. And then you can easily see that this is in the context of regression, because of this structure, this is equivalent to estimating this quantity. And if you think a little bit about this, 2 columns of x could be very close to being collinear, but x theta star is still well defined. So if I even have like a rank deficient x, so x theta star, so I can like shift weights from one theta to the other, but it doesn't change x theta star. Basically, the span of x, like the column span of x, is well defined even if some of the vectors are collinear. So this suggests that estimating this quantity is much easier than estimating theta hat minus theta star itself. So you saw that we need RE condition to translate bounds on this, like lower bound this by theta hat minus theta star. If I don't have to do that, I could guess that maybe if I just care about this, I don't need the RE condition. And that's true. There are examples. I'm not going to go over the proof. The proof is simple. Uses the same techniques that we discussed. So you can say, like, state a result like that. So for the Lagrangian lasso with lambda being bigger than this quantity, which we've seen before, then you would have any optimal solution would satisfy this bound. And this doesn't require an RE condition. However, if you have a sparse vector and you have the K3 RE condition, then you get a slightly better bound. Instead of lambda, you get lambda squared. This is similar to what we had for the theta hat minus theta star. But this is interesting. So you can say something even in the high dimensional regime without the RE condition. Okay, and if you translate these, so you recall this has a certain scaling. If the columns are normalized and let's say we're dealing with sub-Gaussian design, so once the dust settles, these 2 bounds give you things like this. So you can show that the rate at which this goes is like root 2 log d over n. The rate under the RE assumption is 2 log d over n. This is sometimes called the fast rate. It's called the slow rate. And you can see if this is going to 0, square root would produce a larger quantity. So this is much larger generally than this. So the analysis shows that, at least this analysis shows that the RE condition allows you to get the fast rate for prediction, but without it, you still have the slow rate. Whereas for the deviation bounds, you don't even have anything. So assuming that theta star L1 like is controlled. That's just the point that is worth remembering. Like in machine learning, you usually care about this. You don't care about estimating the actual parameters. And in statistics, people care about estimating the parameters because they think that the model is correct. But if you don't care about the parameter itself, I mean, as long as you're predicting well, then these things could succeed under much milder assumptions. Okay. Is this clear? Sort of. So that's the prediction business. There's another thing that you can ask, which goes in the opposite direction in terms of the hardness. Is now suppose like theta star is actually S is sparse. Can I actually recover the support of theta star? So when I solve this lasso solution for the lasso solution theta hat, can I say that, so I'm going to skip the proof. The proof is short. So you can I say that we can recover the support? Basically, can I say that with high probability, the support of theta hat is equal to the support of theta star? So let's say this goes to 1 as the parameters go to 0. The support is the subset that is non-zero. Sometimes this is referred to as exact recovery or the model selection problem for Lasso or the value of selection. So we have like these deviation bounds for the parameters, prediction bounds, and then model selection problem. So that's a harder problem because you want to say that the support of theta hat is exactly the same as theta star. But Lasso produces a lot of zeros, and you might guess that under certain conditions, the zero pattern actually matches exactly with the zero pattern of theta star. And indeed, you can show something like this. The issue is that you need a very strong condition. So the one condition is that this is mild. So this is saying that the SS block of the sample covariance matrix, if you recall our definition, sigma hat, this sigma hat SS, sigma hat is 1n. X transpose. If the x's are 0, mean this is an estimate of the sample covariance matrix. We're saying that lambda min over a block of size s is controlled, which is if s is small, this is reasonable. This is like similar to the RE condition. It's even milder. But there's this other condition which is called mutual incoherence. I'm not going to go into it, but it's just measuring how much correlated the columns are. So this is basically, if you think about this quantity, this is like regressing xj onto the columns xs, if you remember the OLS estimate. So I'm regressing xj onto, so you have like, let's say the true support. This is the true support. Maybe true support is very small here. So I have the true support. And then I have like, I pick any other column that's not in S. So for any J that's not in S, so J belongs to S complement, then I regress this column onto these, do a usual OLS regression. Let's say support S is much smaller than N, so I can do a regression. So OLS regression of xj onto xs, and then this would give me the estimate xs transpose x inverse xs inverse xj. So I want this to be small. Basically, this is saying that this column is not that correlated with this. But then I have many of these. So I want basically all of them to be uncorrelated. You can imagine that if one of these columns is highly correlated, then I can move some of these thetas to that column, and then I make a mistake. Okay, so in order to have like perfect recovery of the support, these other columns have to be really uncorrelated or orthogonal, basically close to orthogonal to S. But this is a very severe condition because we have a very large number of them. So the exact condition turns out to be this thing. So this is the L1 norm of the matrix. Oh, actually, no, this is the L1 norm of the vector. And you can write it as an L1 matrix norm as well. But this is saying that the L1 norm of those OLS coefficients, the maximum over S complement, this is bounded by alpha, where alpha is strictly less than 1. I have it somewhere. Yeah, so for some alpha, that's strictly less than 1. And you can say that this is, you can prove that this is sort of necessary and sufficient. So if you recover, this has to hold with alpha less than or equal to 1. And if this is strictly less than 1, then you recover. So almost like up to the boundary, this is necessary. And this turns out to be really severe. So if you think about like a correlated random design, the correlation has to be very small for this to happen. So I'm not going to prove this. This is called mutual incoherence, but if you're interested, if you have time, if you really are interested at the end, we can come back, or you can take it as a project and try to prove it. The idea is using, so this is again, just the overview is like you prove a theorem, which is deterministic, and then you verify the conditions stochastically. The proof is using a technique which is called often primal dual witness construction. So the idea is to basically, the lasso is a convex problem. It has a dual, and then you guess what the solution is. So because you want the solution to have the true support, you assume that the actual solution of the lasso has the true support, and then you solve the regression basically, or the lasso over the support. That gives you the actual coordinates. That would be your solution, and then you try to find a dual variable that together with this primal solution satisfies the optimality condition. They're called KKT conditions. This condition allows you to find the dual variable, and then you have a nice result that says that under this condition, there's no false inclusion. Under this other condition, there's no false exclusion. Overall, you would have there's one part requires more conditions, so there's also a sort of what is called the beta min condition. So you need theta stars or the support to also have a strength. So if these guys are uncorrelated, but one of the theta stars is very small, I might miss that column. Because you also need that condition, which is called the beta min. So minimum theta star or the support should be bigger than this quantity. And then you can verify, like recast this in terms of the stochastic things and get a nice result. Yeah, in the end, the story is, I don't have the story, but the thing is that with high probability can recover, assuming a beta min condition and this mutual invariance. I'm going to skip it because it's again, a little bit involved, but you can follow it from the book. If you have questions, let me know. If you're really interested, we can go over it in details. It requires some interesting convex optimization machinery. Okay, so that's the end of this chapter. Yeah, these are all the proof of that result. Okay, so we're going to end here. Any questions? Okay, so next time we're going to come back and talk about like chapter 5, which is metric entropy. So these are nice ideas. It's a change of topic, and then talk about random matrices. Okay, sounds good. Thank you. See you next time.